Okay, so it's Thursday. I'm going to do 2 lessons today. I'm going to do equations of motion for constant acceleration, which is quite a quick one. And I'm going to do motion with variable acceleration. Okay, so this one's from page 184, section 7.3, motions of equation for constant acceleration. This, you've probably seen this before in your first trimester, if you attended that one. So key point, the following are quantities involved in motion problems. We can have S for displacement, U for initial velocity, V for final velocity, A for acceleration, and T for time. You might have heard of these as the SUVAT quantities. Okay, look, I've gone off it. It's in the notes already. For constant acceleration, these quantities satisfy 5 equations, sometimes called the SUVAT equations. You need to memorise these equations and know to derive them. Well, I'd say at this stage, you just need to memorise them. Because they're not given in your exam. Deriving them, that's the sort of thing teachers have to do. Although you might have to do that next year, but you definitely don't have to do it this year. Each one involves 4 of the 5. By that it means 4 of the 5 displacement, initial velocity, final velocity, acceleration or time. So each equation has got 4 out of 5. So if you've got 3 of them, you can always work out the 4th. Okay, or if you've got, So, yes, and when solving a problem, you should list the variables you know and the variables you want to find. Then you choose the correct equation, the one with 3 of the known and the one unknown. Okay, so acceleration, just seen this in yesterday's lesson. This is the gradient of the velocity time. That's not v minus t, that means velocity time graph. And so the acceleration is the change in velocity, because it's the gradient. Remember the first one, velocity, that's vertical, time is horizontal. So it's the change in the vertical, change in velocity, v minus u, over the time taken. And then they rearrange this, multiply both sides by t, that's going to give you the AT. AT is v minus u. And then add u to each side, v is u plus AT. Okay. Displacement is the area under the velocity time graph again, because these are velocity and this is time. And the way that it looks is, so if you've got, it comes from this one, it's a trapezium, a half. Oh, that's the one annoying thing about my iPad. Nothing else is annoying apart from that one thing. A half, u plus vt. That's u, that's v, and that t across there. It's the area of a trapezium. I don't know if I've told you this. Half the sum of the parallel sides, there we are, half the sum of the parallel sides times the distance between them, that's t in this case, that's the way the formula goes for the area of a trapezium. Now there was a nursery rhyme that my parents told me like a long time ago, last century. Something like half a pound of twopenny rice, half a pound of treacle. That's the way the money goes round, pop goes the weasel. But I don't believe people seem to know what that is anymore when I tell them it. But if you do, the area of a trapezium sort of sings along to it. So it's half the sum of the parallel sides times the distance between them. That's the way the formula goes to the area of a trapezium. Okay, so it's half u, in this case, well, half, in general, it's half a plus b times h. If you've got a trapezium like this. And actually, in general, you haven't necessarily got a straight line there. So it's half the sum of the parallel sides times the distance between them. There we go. So that's a general trapezium, a bit like a roof of a house, but it can even be, doesn't have to be symmetrical, like we quite often draw roofs of houses. Okay, key point 3. So let's keep an eye on what we've actually got doing here. We do that purple. We don't like that purple very much. I like that one. V equals u plus AT. equation number 1. S equals a half u plus v times t, equation number 2. So the first one's got a u, a v, an a and a t. Okay, so if you know 3 of those, you can substitute those 3 in and work out the 4th. Similarly, key point 2, S displacement is a half, brackets, u plus v, close brackets, times t. So if you know 3 of those bits of information, you can work out the 4th. Okay, key point 3. Substituting for v from key point 1 into key point 2 gives, so this v has gone into there, look, key point 1, v is u plus at. So put u plus at where that v is. So it's half u plus at times t. So S equals, right, there's a few steps in there. So this is a half of 2u plus at. So it means that S is a half u plus, and then times t on the outside. Now, multiply the half through. I think we can, a half of 2ut, let's multiply the t in first of all, plus at squared. And then we can go to that one there after this, because a half times 2ut is ut, and a half times at squared is a half at squared. Okay, so this one, key point 1, v hasn't got an s. Key point 2, this one hasn't got an a. Key point 3 hasn't got v because we've substituted it out. Right, key point 4. Rearranging key point 1 gives a u equals v. So key point 1, v equals u plus at. So subtract at from each side. V minus at is u. Okay, and then substituting that into key point 2. So instead of replacing the v like we've just done, we replace the u. So it's a half. Instead of replacing the v is now there. And then we've got, no we haven't, it's u is v minus at plus v times t. So that's instead of the u now. So you multiply out vt and then a half. Oh no, we've got 2vt times a half is vt. And then minus at squared with a half is minus a half at squared. Okay, so a little bit more colouring in to do here. Key point 3, there's an important one. Key point 4, there's an important one as well. And then the last time, rearranging key point 1 for a t this time. So they've had one method, they've started off with these 2 equations, and then they've used the first one to substitute into the second one every time. I've seen these derived in lots of ways, but this is quite a neat way, because it's just one equation into the other 3 different ways. Right, so rearranging key point 1, which was v is u plus at. V is u plus at. So therefore at is v minus u. So therefore t is v minus u over a. And then they've put that into key point 2. So here look, key point 2, a half u plus v, and they replace the t this time by v minus u a, which is there, look. So there's the half. Half u plus v, that's from the original equation. And t is v minus u over a. Okay, so if you can see where that comes from. I think you can, it's just all put together into a single fraction. So when you multiply out the top there, we get, right, so this implies S equals uv plus v squared, uv plus v squared, plus v minus u squared. uv plus v squared minus u squared, and we've also got that one times that one. So look, it's each of these times the first one. No, I've done this wrong. The first one time, the first one in there, that times each of them, and then we want that times each of them. That's the one that we want there. Minus UV. I knew what I wanted. I just wasn't getting it. So it's that divided by 2a. And then look, those cancel. And if we multiply both sides by 2a, we'll get v squared minus u squared from the right-hand side is 2as, which then goes to say, add that over there, v squared equals u squared plus 2as. Right, you never have to reproduce all that, so you just need to memorise those 5 equations. Believe it or not, they do become easier to memorise as you practice with them. Okay. Little paragraph here of notes. So in problems, the moving objects are usually treated as particles with a small or irrelevant size. Okay, so that means that things like air resistance or some other external forces won't really affect them so much. It's more like air resistance, I think. But if we've got a large object, such as a bus, moving short distances, the true distance may be shorter than that used in calculations. Okay, don't worry about that. Don't worry about that. They work best for particles. Right, examples now. An object travelling at 15 metres per second, to me that means u is 15. Acceleration is 3 metres per second squared, and t time is 5 seconds. Work out v. So look, we've got u, a and t, and we want v, and that's the one from key point 1. v equals u plus at. So therefore v is 15 plus 3 times 5, which is 30 metres per second. And then displacement. So again, we've got u, this is part B. U is 15. I'm happy with all the units. They're all metres and seconds. So it's just going to be the standard units, metres and seconds. A is 3, T is 5, and we want S. So it's going to be, S equals, going for the rubber there. Let's get some of this closed down. S equals, when we've got U, A and T, that one is actually key point 3. Oh, I'm on the rubber still. So that one was key point number 1. This one is key point number 3 above. S equals UT plus a half AT squared. So it's 15 times 5 plus a half times 3 times 25. So 15 times 5 is 75. 1.5 times 25 is 37.5. So it's 112.5 metres. Okay. And that's those two done. Number 2. A hot air balloon is drifting in a straight line, constant velocity of 3 metres per second. That means it's starting off at U is 3 metres per second. A sudden headwind gives it an acceleration of minus 0.5 metres per second squared. So this headwind is slowing it down by ½ metre per second every second. And the time period is 16 seconds. For this period, calculate A, resultant displacement. So we've got U, A and T. So it's going to be S equals UT plus a half AT squared, which is 3 times 16 plus a half times minus a half times 16 squared. 48. 16 squared is 256. It's minus because of the minus that's in the equation there. And a half times a half is a quarter. So it's So it'll be 48 minus, and then 4s into 25, 6 remainder 1, 4s into 16 go 4, so it's minus 16 metres, so it's going to set it back 15 by 16 metres. So the distance travelled is, right, so what happens here with this distance travelled, the acceleration is minus a half metres per second squared, okay? So it starts at 3 metres per second squared. It's still going to go forwards until it's the wind makes it slow down to 0 metres per second, and then it makes it go backwards. And it ends up at minus 16. So basically, we've got that from part A that it ends up at minus 16. So we need to work out this distance here and then double it up. Okay, because it will go forwards until it gets down to 0 metres per second, and then it will keep going backwards until it ends up at minus 16 metres. Okay, so if U is 3 metres per second and V is 0 metres per second, and the acceleration is minus 0.5 metres per second squared. Okay, and we want the S. So we've got V squared equals U squared plus 2AS. So 0 squared is 9 plus 2, so it's minus 0.5 times S. So 0 is 9 minus S, so therefore S is 9 metres. Okay, so the wind that's making it slow down by 0.5 metres per second wins out after 9 metres, and it causes it to come to a stop. And then it goes backwards, so it's going to go backwards, it will go forwards, then backwards, and then back to minus 16. So the total distance is 9 plus 9 plus 16, which is 34 metres. Right, example 3. Wait a second. Oh. Right, example 3. Car P is accelerating at 2 metres per second. Let's write that down. Acceleration 2 metres per second squared. When its velocity is 10. Okay. It is overtaken by car Q, which is travelling at 16 metres per second and accelerating at 1 metres per second. How long will P take to catch up with Q? Right, so this feels like I need a different sort of problem altogether. Need a bit more of a diagram here. So car P, we'll assume it's travelling in a straight line. So car P has got acceleration 2 metres per second squared. Acceleration is 2 metres per second squared. And its velocity is 10 metres per second. I'm going to call that U now, because it's at that point. We've got Q comes along. Q is also on the road at the same time. And it's travelling at 16 metres per second. And acceleration is 1 metres per second squared. Okay. So what we need to do, let's just check I've got all that right. Yeah. So look, the difference is this one's going faster because this one's going at 16 and this one's going at 10. So it will overtake it. It will be from here, and because it's going faster, it will overtake it. But it's got a smaller acceleration. So this one's going at 10, but the acceleration's bigger, so this one will catch it up sooner or later. Okay. So what we can say, somewhere down the line, so this is at the start. And somewhere down the line, they catch up again, Q and P. Okay, so this will still have acceleration 2 meters per second squared. This will still have acceleration 1 meters per second squared. Okay, this will have a new velocity that we don't know what it is. This will have a new velocity that we don't know what it is. But it's when they're at the same again. Right, so we can say, if we look at the t is going to be the same for both, because when they catch up, it's going to be the same. So let's call t capital T. Okay, right, so we've got A, U and T. So we do the displacement for P. Displacement S equals UT. I'm going to use S equals UT plus a half AT squared. So S equals 10T plus a half times 2 times T squared. And we do the same for Q. S equals UT plus a half times A times T squared. SP 10T plus T squared. SQ equals 16T plus 0.5 T squared. There's a 0.5 there. Okay, so but actually when they meet again in the same time span, SP is the same as SQ. Oops. So therefore T squared plus 10T is 16T plus 0.5 T squared. So take half a T squared from each side. So it's T squared, a half T squared left there, and take 16T from each side. Minus 6T is 0. Multiply everything by 2. T squared minus 12T is 0. Factorise. T times T minus 12 is 0. So therefore T equals 0, which is what we know because that's over there. But over here, this is going to be the next one. T equals 12. So how long will it take? 12 seconds for them to catch up again.